Welcome, IED, Project Lead the Way students at Lake Travis High School, and anyone else watching this video. Hopefully it's millions and millions of you by now. Today we're going to talk about mathematical modeling, which is finding out the relationship between two variables, two numbers that can change value, and putting that relationship into mathematical terms. So let's jump right in. This lesson is flipped. All my students should be watching this on Edpuzzle right now, hopefully at home before you come to class Friday or Monday the 7th or 10th of December. Let me talk about this really cool thing. I've started to implement these news articles in my lectures. I really like this one. The Riemann hypothesis might have finally been solved, which is really cool. This was a problem that has been plaguing mathematicians, and I thought it was appropriate because we're talking about math, for 100 years or more. This was several hundred years actually. This was a problem that David Hilbert presented as a millennium problem at the turn of the 20th century in 1900. So in 1900 he posed this set of problems that if solved they would be rewarded $1 million and given this Millennium Prize. So this is one of them, the Riemann hypothesis. This stuff over here, domain coloring, that's related to it, the Riemann zeta function. But yeah, some guy came out. You can click on this link to view this article, but some guy came out and said that he might have finally solved it. So crossing our fingers, seeing if this is actually the solution. People have dedicated their entire lives to solving this particular problem, and it might be all over for them. So pretty interesting stuff going on right now. These are some announcements for what to do when you get into class. Here are some other announcements. Extra credit modeling project is live. Go check the assignments on Schoology under Unit 4 for that. Okay, so today this is what we're going to do once we get into class. We're going to do this worksheet and cut it out, tape it in our notebook, take pictures of it, submit those pictures to Schoology. Sorry, it's a little convoluted, but I think it's going to be better for all of us in the long run. So the first thing we're going to talk about is modeling as a whole. Modeling is a very important, very powerful concept out there in all kinds of disciplines of math, science, philosophy, you name it, all kinds of schools of thought. Modeling is taking a complex idea and boiling it down to a simpler concept, a simpler understanding of it, a simpler relationship, for instance. So you can model lots of different things in lots of different ways. These are the 5 main models. I would recommend writing this in your engineering notebook. Concept modeling, graphical modeling, mathematical modeling, computer modeling, physical modeling. Let's fly through all of them. Concept modeling is just getting the ideas in your head. Like when you design a theme park, you get these ideas. Obviously, it's going to be way more complicated than that with trash cans everywhere, right? And the distance between certain roller coasters, a certain described distance, dimension. And the concrete made of a certain type of concrete. All of those details are out there in reality, but whenever you create the concepts first, you can whittle it down to simpler ideas. Okay, here's another concept, solve global warming. Obviously, there are more than 5 things, 5 ways of doing it. Obviously, there are more than 5 sources of this problem, but this is a simplification of it. Graphical modeling obviously creates an image that you can view in a short period of time. So when you map the ocean floor, you've got all these trenches and stuff. Obviously, it doesn't look exactly like this, but we choose a resolution that makes sense to this scale, okay? We choose a resolution that makes sense to this scale. Maybe in this trench, there are lots of other little tiny trenches too, but they're obscured by just this one line. We've chosen a specific resolution that makes sense at this scale. We don't have to show everything when we give a global map. Okay, let's keep going. Other graphical models are sketches and drawings, charts and graphs, and now mathematical modeling. Tell me, do you think that this equation, v equals pi r squared times h, is a perfect equation to represent the volume of a cylinder? What do you think? Okay, yes and no is the right answer. Yes and no is the right answer. Yes, it will perfectly describe a perfect cylinder, but in the real world, there are lots of deviations from this perfection of a cylinder. So yes, in our abstract mathematical world where we do have these perfect cylinders, yes, this model is adequate. It's all the way complete. But if you were to have a real cylinder like this, there are some deviations in this coffee cup's cylindric nature, right? It tapers off down here, and then it actually gets a little bulbous in the middle, et cetera, et cetera. And then if you did try to construct a perfect cylinder, the dimensions would be off by a little bit, or whatever your tolerance is. And down to the atomic level, you can't make a perfectly flat surface. So you'll have some deviations, you'll have some error from this model, but the model is a simplification, and it's a very good one at that. Here's a good model here, good simplification of this data. In this case, this is what we call inductive reasoning. We're going from the data out there in the world, and we're trying to create a model out of it. Okay, we're trying to see a pattern, and then see that shape. Let me see. I'm a little backwards from where you are. Anyway, that shape. That linear curve, we can call that, and we'll get to that in a second. That curve comes out of our data. We can say our data fits this kind of curve that we've created. So this is a really cool mathematical model. Computer models are anything that you can simulate in the computer. You can simulate a little slice of reality in the computer in all of these ways. 3D modeling, obviously we're not simulating everything down to the atomic level, just the general shape. Structural model, you can simulate forces on your object and how those forces are distributed and dispersed. You can simulate circuits. Circuits can be systems that take some input of signal and produce an output of signal. We can model that as a function too. We'll get to that in a sec. And then computer-aided manufacturing. We can talk about how to manufacture all of that. We can tell the computer specific instructions. Okay, and then we've got physical modeling. 3 kinds. Scale, this is a house built to scale. Mock-up, which is just a general looks like model, which we've talked about before. And a prototype, which is a general works like model. It generally works like how we want the actual thing to work. For example, it's our first iteration of the production process. It's not how we're going to manufacture on an assembly line, but it's the first iteration of that process. Okay, let's talk about linear functions. First, we got to talk about functions themselves. We got to talk about functions. A function is, I really like this definition, it's a rule that takes an input, transforms it, produces an output. Or if you're looking at the mirrored image here, takes an input, transforms it, produces an output. Okay, and that's a really, really cool definition because that concept of function can apply over and over and over to lots of different systems. Like I said, a circuit, a node in a circuit, maybe a resistor or an LED or even a computer itself, can take an input, a signal, whether that's current or voltage or anything else. It can take an input, change it in some way, produce an output. That's a function. Your body, you can take inputs of sugar, insulin, whatever you take, and then your body will do its magic and produce an output, which is the blood sugar. For instance, you can model your body as a function. So it's a really, really cool idea. It takes inputs, produces outputs. Those inputs are what we call a domain. The domain is the set of all inputs, and what we have on our outputs is what we call the range. In this little scenario, y equals 5t plus 3, we want our time to start at 0. Negative time, it's kind of a weird conception. Maybe if you said that time t equals 0 is whenever I walked in my room. Whenever I walked in my room, and then I'm modeling stuff after, the distance, maybe I'm walking away from the door, and the distance increases linearly constantly as time passes. And maybe you can talk about negative time, like maybe before I got to the door. But generally time t equals 0 is what you're interested in. The time starting from what we're interested in until forever, maybe. So generally time starts after 0, and then range is that y-intercept and onward. Okay, we'll talk about all those concepts in a bit. So a linear function is a function with inputs you plot on the x-axis, on the horizontal, and outputs, which you plot on the y-axis, the vertical. A linear function has these inputs and outputs and has a constant rate of change between them. So that means whenever you change a unit, whenever you increase a unit of your input, you output a certain amount. You change your output by a certain amount. So whenever you change your input by a certain amount, like 1, your output changes by a certain amount. And that certain amount that it changes by is constant, no matter where you are in your input or on your x-axis or in your independent variable. No matter where you are, that change is constant. And you can tell because this change, I go over a little bit in the x direction, and then my curve goes up a little bit in the y direction. If I go over a little bit over here, then my output goes up a little bit as well. So you can see it's not changing however much it goes up rather, if I go over by 1. But if I went over by 1 here, and it would happen to jump up way up here, then that rate of change would be changing. The rate of change would be changing. Yeah, the rate of change would be changing, and it would no longer be a constant rate of change, and it would no longer be a linear function. So rate of change is also called slope. Rate of change is also called slope. We need a constant slope, or that makes a line. It looks like a line, so that's why we call it a linear function. All right, let's skip forward. Oh yeah, I forgot to mention back here, with functions, you can represent them in multiple ways. A function is still a function. This y equals 5t plus 3 is still a function no matter how you represent it. With a table, with a graph, and with an equation. It's the same function, just represented in different ways. The table, the graph, and the equation. So with this one, you've got the independent and the dependent variables like we talked about. And for every time you increase your x by 1, your y increases by 4.5. That's what this means here. A change in x by 1 reproduces a change in y by 4.5. That's a constant rate of change. Okay, here's a table of data. You plot this data by going over from the origin by however much that is. 2, you go over 2, and then you go up from the origin by however much this is, this y. You go up this way. Okay, so 2 by 13, and this here is an ordered pair. It's similar to a vector like we talked about last time. Similar to a vector, you can represent a vector with 2 numbers like this. But this, in this case, represents a point, not a vector. You have to be specific about what you're talking about. A point, not a vector. So this is a data point that you can plot with an ordered pair. Okay, and here's our equation like I talked about. If I go over by 1, I'm moving up by 5. You can calculate the slope by rise over run. How much do I rise from this point? I rise 5, and then how much do I run to get to the line again? All right, I run by 1. So it's 5 over 1, which is 5. Now, with linear equations, you can always calculate the slope no matter what 2 points you select. You can always calculate the slope no matter what 2 points you select. That's a property of linear functions. Now, if it's not linear, like a parabola, you cannot calculate the same slope when you pick 2 points. That's why in activity 3.3 it said, what is the average velocity being slope, what is the average velocity between time t equals 2 seconds and time t equals 4 seconds. Excuse me, when it was a parabola, it said that. Now, when it was a linear function, it just said, what is the average velocity at one particular point? 3 seconds, for instance. And you're able to do that because that slope at this point where my mouse is the same slope throughout the entire curve. If it was a parabola, if it was curvy and not a line, then the slope would be changing. So at 3 seconds, it might be something different than at 2 and at 4. But in between those two, between 2 and 4, you can do the rise over run, change in y over change in x, and get a straight line model out of it. You can calculate the average rate of change by a straight line model. That's what the change in y of change in x is. Okay. So let's talk about function notation. This is a really cool notation to describe functions. It's a big letter talking about the function itself as an entity, a property. The whole thing is a function, that big letter. And then parentheses takes in your input. What's inside parentheses is your input. So you read this like big G, or you don't have to say big G, you could just say G. G, and you read this like this, of t. So this is called G of t. That's a function, G of t, where G is the output and t is the input. And I really like this. I'm a nerd, because this looks like it's a box or a machine, and I really like that analogy to functions, because you can imagine functions as machines that change something. So if I take a machine, if I have a machine, and then I add in some stuff, I want the machine to change it and produce some outputs. And this function is going to do that in the same way no matter what you put it in. It's going to produce that output in the same way no matter what you put it in. So you put in the t's and out come the g's, okay? You put in the t's and the g's pop out. And if you have this function here with an equation, you can plug in the t, whatever the t is, and then you'll get a specific value for the g. Okay, so like I said, this is the function notation here. And there are some other details about this particular function that we'll get into later. Okay, for your first question, we're going to use this function notation to analyze a certain curve. This is our curve. Here it's represented by this function b of t equals 5t plus 3, which means this number right here is the slope. Every time we move up by 1 second, we increase by 5 feet. So that is 5 feet per second. Slope, the toy car, if this is the distance of a toy car, moves 5 feet for every second of time. Good. And the y-intercept is 3 feet. So we add that plus 3 at the end when we calculate this function. The toy car is initially 3 feet from the starting line at time t equals 0 when we start timing the thing. Okay, so I want to ask you, what is the distance at t equals 6 seconds? Now remember, this t equals 6 seconds is just a value to this variable. It's a value to this variable. So this variable is here inside this function. We're going to plug that in. We're going to substitute that variable out for this value and then see what our function does to it. So again, what is the distance at t equals 6? Okay, if we do that, we plug in the 6 right here. We plug in the 6 as the t. We substitute it in. We substituted in the 6 for the t. And you can, when you do that over on this side of the equation, you can do it on this side too. So 5 times 6 is 30 plus 3 is 33 feet. And you can do that here graphically too. You can look and see where my time equals 6, go up to the curve, and then you'll go over to 33 feet. Okay, another question. When, that is what time, at what time will the object be 23 feet from the line? At what time will the object be 23 feet from the line? Okay, yeah, if you go and look at 23 feet on the distance, 23 is the distance, you can substitute in 23 for the distance. That whole thing, d of t, distance there, becomes 23 in this equation. And then you can use algebra to solve this equation. 23 minus 3 is 20, divided by 5 is 4, so t would equal 4. You can do that graphically over here too. 23 here, go to your curve, go down, and you'll hit 4. All right, a couple of different ways to solve something like that. Now, let's talk about quantifying correlations. Okay, let's jump back to this slide. Like I said, when you have data, you can plot your points on a grid like this. This is a Cartesian grid. Don't worry about that so much. But when you do that, you come up with a scatter plot, because this is all real data, for instance. This is all real data, and you're putting a plot in it. Whenever you create a mathematical model like we talked about earlier, we're trying to see if there is a relationship or if there's a trend in the data and come up with that model ourselves. So just to be clear, this is not your linear function. Your data is not your linear function. We're trying to create a linear function that matches the data, that represents the data. Okay, so when we do that, we can start to quantify this correlation here. We can start to quantify different measures of how well this linear function does represent our data. We can do that with this value here, correlation coefficient, otherwise known as R. R always has a value between -1 and 1. So whenever that value is 1, that means we have a perfect correlation. That means all of our data lies perfectly on a line. And that's not going to happen unless you have some fabricated example. Or if you're simplifying your data and rounding, maybe, for instance, you might have something right on the line. So positive or -1 is a perfect correlation. I should note, a negative R just means a negative slope. Negative R means a negative slope. So if it's perfectly positive, your data is perfectly positive, your R value of this trend line that you create ends up being +1. If it's negative and it's perfect, it ends up being -1. This is showing a negative correlation. You can say that, negative correlation, when your value is -1 for R. When it's +1, it's a perfect positive correlation. When it's positive anything, it means it's a positive correlation. We'll talk about strong and weak down here. And when it's negative anything, that's a negative correlation. 0 is no correlation. That means your data is so random that this trend line that you create ends up not matching at all. And that's almost impossible to get exactly 0. But it is possible to get very, very close to 0, which means your data is just kind of random. There's no relationship, there's no trend, and that's important. That means your dependent variable is not actually causing a change in your independent variable, or vice versa, rather. Your changes in your independent variable are not causing changes in your dependent variable, which is good data to have. It tells you that there's no relationship there. Okay, like I said, positive is a direct or positive correlation. Negative is an inverse relationship or a negative correlation. And then here's the strength. Normally, this is how we talk about it here. Greater than 0.8 is strong correlation. Less than 0.5 is a weak correlation. Okay, now that's just a convention, like many other things. If it's 0.79, if you have a correlation coefficient of 0.79, can you make the argument that it's strong? Yes. But it'll be a tough argument to make, okay? It'll be a tough sell. You can make that argument, sure. This is just a convention. You would actually have a hard time making an argument that your relationship is strong and direct. If you have a R value of 0.85, for instance, you can make that argument, but you might not convince everybody. If it's something like 0.96 or 0.99 even, yeah, that's very convincing. You can definitely make that argument. You see what I'm saying here? These are all conventions, though. All right, another method of determining how strong your correlation is this coefficient of determination, which is very similar to the correlation coefficient. It's the same letter for the variable. No coincidence there. The coefficient of determination is R squared, whereas the correlation coefficient is just R. So to find the correlation coefficient from the coefficient of determination, what do? Right, you just take the square root. You take the square root of coefficient of determination, and that pops out the correlation coefficient. And to go the other way, if you're given the correlation coefficient, you want to find the coefficient of determination, you just square it. Easy. Okay, so this tells you some slightly different information. Of course, if you square a number, it's not going to be negative. So your values are always going to be from 0 to 1. And it has this interesting interpretation. It tells you what portion of the variance of one variable is predictable from the other. So for instance, if you get a value of 0.65, then you can say 65% of the variation in x is due to changes in the variation in y is due to changes in x. 65%. The other 35% is from whatever. You know, we have lots of complicated relationships. We have lots of changes in our world. We have very, very interesting, very complex relationships between lots of different variables. You have multivariate systems going on. And so maybe only 65% of the variation is due to x. Okay, this is a pretty cool interpretation there. And like I said, it's the square of the correlation coefficient. All right, so the next section is finding trend lines, which is what we've been talking about, finding those trend lines. These slides talk about how to do it in Excel. And you can go back through all these slides if you want to, but I'm going to demonstrate how to do it in Google Sheets. Okay, here's my sheet here. I just created some random data, or I got it from Project Lead the Way rather, of sales in these fiscal years. A lot of times, in order to quantify a fiscal year, you don't want to put 2003. That'll give you some really interesting looking graphs. You want to change that. You want to change your index to be 1 at whatever year you're starting at. Okay, so we've defined the year 2003 as year 1. I've left it like this for an interesting reason, because on Google Sheets, and I think Excel does the same thing, if you select if you select one cell and then try to click and drag, it'll just copy the contents of that cell. But if you select 2, and I did that with Shift, if you select 2, it'll try to guess what kind of pattern you're doing. And yeah, my pattern was just going up by 1 each time. So I want to do that for both. And I can do that for both of these 2 rows, these 2 columns at the same time. Bada bing, bada boom. There we go. So copy this into a new spreadsheet. Copy this all into a new spreadsheet for you. Okay, so now if you've done that, we can talk about how to create a trend line. So first we select the data. We select our data. We select our data, and then we insert a chart. Insert a chart. Now it's going to guess what kind of chart you want to use. We don't want a bar chart. We want this one right here, scatter plot. Scatter plot. So I can go back and do that a little slower if you want me to. Select our data, insert chart, and now it pops up data, chart type. We want scatter plot. Okay. And so we get our trend here, our trend line here. So we have something between, 2.3, it looks like 2.3 is kind of our low end, $2.3 million, and between that and like maybe 3.2 looks like the max, 3.2 something million dollars. So our graph right now doesn't look that great. It's kind of confined to this tiny sliver of our graph. Our data is kind of confined to that. So we want to customize. And let's customize the vertical axis. Let's customize the vertical axis to give us a certain minimum value. Like we said, the minimum it looks like was 2.2 or something. Let's just make that 2. Yeah, now that looks a lot better. And then we can make this up here 3.3. Okay, that looks pretty good too. But I kind of want it to be rounded to maybe whole numbers. So maybe I can do 2.2, 2.1, let's see, all the way up to 3.4. How will that look? Maybe 3.5. Okay, that looks a little better, 3.5. Now we've got solid lines on the top and the bottom, and then we can add minor grid lines to those as well. Let's just make sure our horizontal axis looks good. The minimum value, I like to start with 0, like I said. That way you have a line at the end, and you have a grid line at the end, and your data is not actually on the edge. That way it'll look stupid. So over here, we want this to be 10. That way we have a line, and our data is not on the edge, but it takes up the whole space. Okay, and now I can add grid lines because I'm missing the 1 and the 3. Also, I'd rather have the 2.1, 2.2, 2.3, 2.4. So that's 1, 2, 3, 4 minor grid lines I want to add there, and 1 minor grid line I want to add here. So on the vertical axis, sorry about that, I want to add 4, like I said. And then on the horizontal axis, I want to add just 1. That way I can tell 1, 2, 3, etc., etc. I can get a better handle on my graph. Of course, you never, ever want to give me a chart or a graph without a title. So I can do sales over, let's see, sales, maybe I can call it sales in millions of dollars over, let's see, maybe between 2003 and 2011. All right, that's a pretty good title. I can, let's see. Yeah, axis title, sorry about that, is under here. Horizontal axis title, I always want axis titles. Always want axis titles. So this is year. I can say 2003. 3 equals year 1, and a vertical axis title. This is going to be sales, and you always want units too. Millions, even if it's a unitless value, you can say parentheses unitless. Okay, sales in millions of dollars. Now we want to add a trend line. So we want to add the trend line to this particular series. You can put more than one series of data, but of course we only have one right now. So we want to add trend line, and you can specify the type. We are only dealing with linear trend lines, but of course if you think that your data is more exponential, making this curve, or polynomial, making this kind of curve, or whatever you think it is, you can create that type of trend line, which we might get into later. But let's add the trend line. We definitely want to add the equation here, and we want to show our R squared value like we talked about. Okay, great. So we have a trend line, we have an equation, and we have an R squared value. Okay, so now that we've created our trend line, we can use it to make predictions into the future, which is really the power of these trend lines. Either predictions into the future or predictions between the data points. Maybe we weren't able to measure between the data points, but we can create that data. We can predict that data, guess about it, using our trend line. That's called inductive reasoning, using what we've got to generalize. Okay, so here's our function that we created, and we put it in function notation. S is projected sales, T is T, and we created a function S of T. Here's our slope that we calculated with our trend line, 0.1335, and here's our y-intercept that we calculated, 2.0269. S is the projected sales, and T is the year number. Remember, we normalized that. It's called normalizing. We normalized that year to make 2003 equal to year 1. So here's a little formula to calculate any other year. If you take your year and you subtract 2002 from it, then you'll get the T that we want. Okay, so we are trying to guess, trying to use this trend line to make a prediction. What is the sales projection for 2015? Now, I'll give you a hint. If you put 2015 into that little formula to calculate T, T is 13, okay? T is 13. So what is the sales projected for 2015? Okay, so you, once again, substitute that 13 out for T, and you can do that here in this function notation. And on the other side of the equation, what you do to one side of the equation, you have to do to the other. So when you do that, you've got this slope times 13 plus the 2.02. That gets you $3.76 million. Okay, another question. When will the sales reach 4 million? In other words, what value of T will you get if your sales are 4 million? Okay, you have to substitute out the 4 for S. Now, be careful. You might have substituted out 4 million for S, but S is in units of millions of dollars already, so we just have to substitute in 4. And then we do some algebra to solve for T. So 4 minus 2 point blah, blah, blah gets you 1.9 blah, blah, blah over the, and then you divide by the slope, 0.1335, and T equals this, which is 14.8. And you can see that graphically. We could have done that in the last example as well. But when your sales are 4 million, you can just go over here to the curve and then drop down until you hit this 14.8. All right, so that's all I've got for you. Hopefully this will be enough information to do all of the activity 4.4. I think there's one thing that I missed. When you talk about domain and range, really what you want to do is you can draw a box around all of your data for domain and range, and then the domain is the interval that the box is drawn around. So in this case, the box might be from 1 to 9. That's the domain. Domain is from 1 to 9, and then range is from whatever it was, 2.2 up to 3.2 or whatever that was. Okay, so that's domain and range. Let me know if there's something else that I missed, and have a good day.